Now we switch to deadlock detection. Now in deadlock avoidance, we were avoiding deadlocks before they happen. So the idea is to avoid deadlocks before they happen. Now we're studying the detection of deadlocks after they happen. Now, which do you think will be easier? Detecting deadlocks after they happen or avoiding deadlocks?
Avoiding.
Avoiding is easier?
I would think, because
It's preferable.
it might be harder to detect that an actual deadlock is happening.
Well, but when it happens, it's when a deadlock happens, you have it actually happening. So your analysis to detect a deadlock will be easier than your analysis of the future, trying to determine if a deadlock may or may not happen. So this avoidance analysis, in your avoidance analysis, you are analyzing the future based on the projected need. But in deadlock detection, you are analyzing the present, what you currently have in the system, and that's going to be easier. Of course, if in theory, if you can avoid deadlocks, avoidance is much better than detecting a deadlock and then finding a way of resolving the deadlock or eliminating the deadlock or recovering from a deadlock. Right, so we always prefer avoidance, but avoidance is harder. Okay. Now, the detection algorithm are going to be similar to the avoidance algorithm in the sense that when we have a single instance of each resource, we use the resource allocation graph. When we have multiple instances of each resource, we use the detection version of the banker's algorithm, which is slightly easier than the avoidance version. Okay, so now with the single instance of each resource, what do? We simply detect cycles in the graph. So, here's an example with processes and resources. Given a resource allocation graph, we can construct a wait for graph. And what does this mean? So for example, P1 is waiting for an instance of R1. And that instance of R1 is held by P2. Then P1 is necessarily waiting for P2, right? Because P2 has the only instance of the resource. Right? If there had been two instances of R1, we wouldn't have been able to say that P1 is necessarily waiting for P2. But P1 is necessarily waiting for P2 because there is only one instance. Okay? It's like you are trying to looking for a book, trying to check out a book from the library, and there is only one copy of that book. And there is one person who has that book. So if there is one copy of the book, then you are necessarily waiting for the person who has that one copy of the book to return it to the library. Then you can check it out. But if there are multiple copies of the book, then you are not necessarily waiting for one specific person. Okay? Here, you are specifically waiting, P1 is specifically waiting for P2. So that's why when there is a single instance of each resource, we can form the wait for graph. So P1 is waiting for P2, P2 is waiting for P5 because it's waiting for one instance of R3, and P2 is also waiting for P3, and so forth. So we form this graph, wait for graph. Now in the wait for graph, if there is a cycle in the graph, that means that there is a deadlock. Now, do we have a cycle in this graph?
Yes.
Yeah, so we do have a cycle. Well, do we have a single cycle or multiple cycles?
Multiple.
Yeah, we have two cycles. We have this big cycle, or the outer cycle and the inner cycle. So we have two of them. Now, if we detect this cycle and we are looking for a process to terminate, we're trying to resolve a deadlock by terminating a process. Which process here would you terminate in order to resolve the deadlock?
The one holding the most resources.
Which process?
P4.
P1.
Okay, P4. So someone said P4. So let's see if terminating P4 would resolve the deadlock. If P4 gets terminated, then it will get eliminated, and all the edges that are incoming or outgoing of P4 will get eliminated. So we will end up with this linear dependence, and that's not a deadlock. So yes, by terminating P4, we will no longer have a deadlock. We will resolve the deadlock. So P4 is one good choice, but it's not the only choice. There are other processes that we can terminate to,
P2?
P2. So if we terminate P2, then you will get rid of P2 and all of these edges. So you will only have this edge, and there will be no cycle. Yeah, so P2, terminating P2 will resolve the deadlock. What else? Yeah.
P3? Or no, sorry, P1?
Yeah, P1. Again, if we eliminate P1, we will end up with this, and this is not a cycle. Okay? So this is not a cycle. So if we eliminate P1, there will be no deadlock. About what is left? P3.
No, because you still have a cycle, P1, P2, P4.
Yeah, exactly. So if I terminate P3, then I will still have this cycle. So P3 is not good. So P3 will not help. Terminating P3 will not eliminate a deadlock. Okay. All right. Yes.
If you eliminated P1, wouldn't P2, P3, actually, never mind, I see it. I was gonna ask, wouldn't that still be a cycle, but based on the edges, it wouldn't.
Yeah, it's not a cycle. So if we eliminate P1, we'll end up with this, and this is not a cycle. This is P2 depending on both P3 and P4, and P3 depending on P4. So, both of them are depending on P4, and there is no circular dependence. So when P4 eventually, P4 is not waiting on any of them. So P4 will make progress, and it will eventually release the resources, and then P2 and P3 will be able to make progress. Now this is an algorithm's question. Which algorithm do we use to detect cycles in the graph?
Is it Bellman Ford?
Bellman Ford is for shortest paths with negative weight edges. So it's more the algorithm that detects cycles is more fundamental. It's a simpler algorithm. So which algorithm detects cycles in the graph?
Message. DFS.
Yeah, it's DFS. Exactly. So DFS is the algorithm that detects cycles in the graph. And so what's the running time of DFS?
Squared.
OV plus E.
Squared? Yes.
V plus E.
Yeah, so DFS, the running time of DFS is V plus E, where V is the number of vertices and E is the number of edges. Now, if the graph is dense, for a dense graph,
Squared.
yeah, for a dense graph, E is of V squared, or in fact it's theta of V squared, and this means that the running time of DFS runs in of V squared time. So it's a quadratic function of the number of nodes if the graph is dense. And what do we mean by dense? What's a dense graph?
Each node connected to each other's nodes.
Yeah, well, a dense graph in general is a graph that has lots of edges. The most dense graph is a complete graph. So what you're describing is a complete graph, which is the most dense graph, the extreme case, which is each vertex has an edge to all other vertices, to every other vertex. Okay, so this is the so it's an V squared algorithm. If the number of nodes is n, then it's an n squared algorithm. So is it faster or slower than the banker's algorithm?
Fast.
Yeah, so it's faster than the banker. So resource allocation, which makes sense, right? This is for a special case where you have a single instance of the resource. So the resource allocation graph method runs an n squared algorithm, while the banker's algorithm is mn squared. So it's slower by m, a factor of m. And in fact, this is n squared only if the graph is dense. If the graph is sparse, then it's going to be closer to O of n.
Do we assume, if we're going into a graph that we don't know anything about, do we assume n squared?
Well, what do you mean by assume? So it's like in the algorithm.
Right, if we don't know if the graph is dense or not.
Okay, so in the, analysis-wise or design-wise? I mean, are you talking about, are you asking an algorithm design question or an algorithm analysis question?
Analysis.
Yeah, in terms of analysis?
Yes.
So in terms of analysis, we should know whether it's dense or sparse in order to analyze it.
Okay.
But if you want to do the analysis conservatively, or if you don't know whether the input graphs are going to be dense or sparse, then you should conservatively assume that they will be dense. You should conservatively assume the worst case. Yeah. Yeah.
For the banker's algorithm, if we can't find a safe state sequence, is that still O of m n squared, or wouldn't it be considerably less?
Well, yeah, if you detect, well, that's the worst case, right? So n squared, that's the worst case. So there is always a good, most algorithms have very, best case behavior that can, where the algorithm may terminate very early. And yes, if you are in this case, if in the first iteration you cannot find a safe sequence, then you will terminate after the first iteration. You just can't find a safe sequence or a process that can you add to the safe sequence in iteration 1, then you terminate in one iteration. So this is definitely the worst case. Yeah. So worst case here from algorithm analysis point of view, right? So not finding a safe sequence makes the algorithm faster, but it's not a good thing. It means that you don't have a safe sequence, and it means that you will potentially have a deadlock.